Okay, so first things first, in organic chemistry, molecules don't just magically transform into other things out of nowhere. Bonds have to break and new bonds have to form. So, what are these curly arrows? Well, you can think of them like GPS for electrons. They track exactly where electrons are moving, where they start, where they end up during a reaction. A super important thing to remember, it's like a golden rule, I just keep it in my head, is that arrows always start at an electron source, like a lone pair or a bond pair, and point to where they're landing. You can never, ever draw them backwards. So, there are like two types of arrows. You can just see them like vehicles. So on this electron highway, there are basically only two types of vehicles. Or arrows, yeah. And you can just tell them apart by looking at the tip. So the half arrow, and if you look closely, the tip only has like one side to it, and it looks like a little fish hook. So this means only one single electron is moving. We use this for stuff like homolytic cleavage, which is just a fancy way of saying a bond splits perfectly down the middle, giving one electron to each side to create these highly reactive things called free radicals. Now let's go on to the other vehicle, the full arrow. This is your classic standard double-headed arrow. This guy represents a whole electron pair moving together. So, two electrons. You'll see this used everywhere for heterolytic cleavage. So, in this case, one atom is greedy and takes both electrons when a bond breaks, or when an electron-rich nucleophile attacks an electrophile. So, we can see this example. Sodium and chlorine. Let's look at the first example on the sheet. It's forming an ionic bond between sodium and chlorine, and sodium has one lonely valence electron, and chlorine really wants one more to be stable. Because it's just one electron moving, we use that little fishhook arrow. It starts at sodium's electron and points right at chlorine. Once that electron hops over, sodium becomes a positive cation, Na+, and chlorine becomes a negative chloride anion, Cl-. And then because opposites attract, they stick together, and boom, ionic bond. Now next up, we have a polar reaction. Hydroxide ion attacking a carbocation. The oxygen on the hydroxide is loaded with extra electrons. It's a nucleophile. The carbon is sitting there with a positive charge, totally desperate for electrons, so it's the electrophile. And for this case, we draw a full arrow starting directly from the lone pair on the oxygen, curving over, landing right onto the carbon. That tells us those electrons are now being shared to create a brand new covalent bond between them. So to finish up, when you're checking your work on a test, just run through this quick mental checklist and make sure your arrows don't look crazy, because mine do.